a transformation between one domain and another is going to be a function, a differentiable function, such that to each uv in the first domain, associate xy, where x is a function of ub and y is another function of ub. So that can be extended to any number of coordinates. For instance, for 3 coordinates will be something like that, where each of the components here will be functions of ubw. So let's find the image of this domain under this transformation. I mean, this particular function. This function transforms each ub in this, meaning that this is the x that depends on u and b, and this is the y that depends on u and b. So let's see what this transformation really converts this rectangle in. This is a rectangle, right? So it's 1, 2, the interval 1, 2 for the variable u, and the interval 0, pi for the variable v. So let's do a sketch of this domain. Let's do the axis here. This is the axis for u, and this is the axis for b. And so we have that in the variable u, the variation is going to be from 1 to 2. And in the variable v is going to be from 0 to pi. Pi is, this is 1, 2, 3, pi will be like here, 3 point something. Okay, so this is pi. And so this is going to be until here. This is then this domain, right? So the rectangle is going to be this one. So, but now let's apply the transformation t, which is this function here, and see in what this thing transform for the variables x and y. So let's take each of the boundaries here and see how they transform in the xy system. So the first one, for instance, this is a line. The equation will be u equals 1, right? So this will be like the whole line here is just a variable u equals to 1. That's the equation of this line. But the v is going to vary between 0 and pi. So we can clarify here that v is varying between 0 and pi here. But then, so if u is equal 1, so then what the transformation is doing here? So we have t of u is equal 1, so we put 1 here, v. So we evaluate here, so we substitute, right? So u is 1 and v is v. So let's put this one here. We're going to have here 1 cosine of v. So 1 times cosine of v is just cosine of v. And here is 1 times sine v is going to be sine v. So this is the curve in which is transformed the line y equal 1. So this is not a line anymore, right? So cosine v, sine v, what describe is a circle, right? It's a circle of radius 1. So we draw this circle here. That will be a circle of radius 1. But considering that v vary between 0 and pi, so it's not going to be the whole circle, but only the circle from 0 to pi. So this line here got transformed in this curve here. So that's the first of the transformations then that we have. Now let's consider this other side here. So this side will be also a line determined by u equals 2, and b still is going to be between 0 and pi here. And so let's do the transformation. T of 2v will be equal to, substituting here, will be 2 times cosine of v, 2 times sine of b. So we got that this line got transformed in something that is not a line anymore. This is also a circle, though a circle of radius 2. So then this is going to be, and again, b is going to be vary between 0 and pi. So the circle is going to be something that looks like that. So we have that, the transformation of these two two segments. Now let's see what happened with the other two segments. So let's see what happened with this segment here. So this segment here is determined by a line also, but now the line is v equals 0. So that will be v equals 0, and we have that the u will vary between 1 and 2. And so when we do the transformation here, so the u is just u, but v is 0. And so when we plug it in here, we're going to have u cosine of 0, which is 1. So that we're going to have just u. And the other one will be sine of 0, which is 0, will be 0. So we have that this segment here got transformed in a segment 2. In this case will be the segment u0, where u vary between 1 and 2. So we have that this segment is transformed actually in this segment here. Well, in the same way, we can see that what happened with on top, that's another line. In this case, is going to be determined by b equals pi, where u still vary between 1 and 2. And when we do the transformation here of u pi, what we get is u cosine of pi, that is minus 1, and so then we're going to get minus u0. So again, it's transformed also, the segment is also transformed in a segment of a line, in this case, minus u0, when this in vary between 1 and 2. So we're going to get that this is just this segment here, where this number here is minus 2, this one here is minus 1, this is 1, and this is 2. So we got that the whole transformation of this rectangle is this region here. So we are going to define now what is the Jacobian of a transformation. So given a transformation as before, the Jacobian is going to play the role in an integral of the differential. Remember that when you do a change of variables in a function of one variable, you need to do also the differential of the change. Well, this Jacobian is going to play that role. And the way to calculate this Jacobian when the transformation is like this, we are going to get each of the components here, the x. So the x is given by the function f. In this case, well, so that is going to be the first row of the matrix. So we are going to get the first component of the change of variables, and we are going to put it in the first row, and we are going to do its derivative with respect to u and with respect to v. And when you finish, you take the second component and you do the same thing, the derivative respect to u and respect to v. And again, this can be extended with any number of variables. If it were 3 variables, you will get a row here with 3 entries, and will be the derivative of the first component respect to u, v, w. And then in the second row will be the derivative of the second component respect to u, v, w. And in the third row, you will get the derivative of the third component respect to u, v, w. Okay, so for example, let's calculate the Jacobian of the change that we just were using before. So the Jacobian is going to be equal to the determinant of, and so we are going to get the first component and do the derivatives here with respect to u and v. So the derivative respect to u here will be just cosine of b, and the derivative of the same thing respect to v will be the derivative of cosine is minus sine, so will be minus u sine of b. Observe that this row is the derivatives of just the first component. And for the second row, we are going to look at only the second component, and we are going to do the same. Derivative respect to u is going to be sine of v, and derivative respect to v is going to be u cosine. And now we calculate the determinant of this, which is the multiplication of these two, which is going to be u cosine square of b minus the multiplication of this, that is going to be minus again u sine v. sine square of b. And so now we have here u as a common factor. This is u cosine square of b plus sine square of b, which is 1, and so this is just u. So the Jacobian of our change is just u. So we can say j, that depends of u and b, in this case was equal to u. And finally, the formula for the change of variables in a multiple integral is going to be similar to the one in one variable, but with the Jacobian playing the role of the differential. So an integral depending on x and y is going to be equal to the integral of the function, but over the transform domain here. Observe that if we have here the domain D, we are going to have here the domain S, so the transform of the domain. And in here, the function is going to be evaluated at whatever the transformation, the image of the function is. And we have to multiply here by the absolute value of the Jacobian. So be sure here that you pay attention to the notation, since the Jacobian itself is a determinant, but this notation here means absolute value. So it's the absolute value of the determinant. Let's suppose that we want to calculate the area of the region between these two circles in the upper half plane. So when we do a drawing of this region, we see that this is one here, this is the semicircle in the upper half plane, and this other one is a circle of radius 2. And so we want to calculate the area of this. That is nothing but the area that we have worked before, right? It's the area of this region here. Observe how complicated it will be to set up the description of this domain, to do an integral in function of x and y. So in function of x and y, we will need to divide this domain, like divided here, calculated in 3 pieces. We will need to say, like first, this domain will be between this function and this function, and then you see that are different functions, right? That in this other piece that will be between this function and this function, and in the third piece will be between this and this. So you will need to calculate 3 different integrals with different domains of integration. Instead, if we can do an integral in this domain, it will be much easier, right? Well, that's exactly what a change of variable is for. So we want to calculate the integral over this domain S of our function that depends on x, y, dx, dy. And you can do it, as I said before, dividing this in pieces and doing all that. Or you can do the change of variables that we saw before. And so this integral, according to the change of variables theorem, will be just the integral on D, where D is just a rectangle that we had described before, between 1 and 2 and between 0 and pi. So just this rectangle, that's what D was. So we can do instead the double integral over D of f evaluated at the change of variable, right? That's what the theorem says. And multiply by the absolute value of the Jacobian, and so du dv. And so this description in D, then it will be much easier than do the description in S. And so the description on D will be just the integral between 1 and 2 of the integral between 0 and pi dv du. And the function that we are going to put here, well, if we are trying to calculate just the area, the function that we are talking about is just the function equal 1, right? That's the definition of area. So we are going to put here the function 1, and evaluated here doesn't make any difference because the function is constant. and multiply by the Jacobian. So in this case, we have calculated before, and that will be just u. The absolute value of u is still u, since we are here in positive values. And then the integral that we have to calculate now is really easy, of u one and two. The evaluation here will be just pi, and so it's pi u du. The integral of u is u squared over 2 evaluated between 1 and 2. This is pi over 2 times 4 minus 1, which is 3 pi over 2. And so by calculating the area this way, we get the area between these two circles, that you can calculate by regular geometric formulas too, right? So the area in the circle of radius 2 will be 4 pi, right? And the area of the circle of radius 1 will be just pi. So the area between the two circles will be 3 pi, and we're calculating just half of them, and so we get the 3 pi over 2. So you can check that this makes sense with what you think that is the area between two circles.